I was asked to put my main focus on gums, as I also used this for my PhD thesis. And I used it for modeling a zooplankton life cycle, which then becomes maybe more in that sense the typical thing of how you think of modeling. I mean, linear regression is usually not something that's considered as sophisticated modeling. But still you can do, like, it shows you a little bit what you can do with those different kind of, with even linear regression or GAM models, for example. And, but I will talk, I think most of the time I rather might talk about linear models than additive models. Okay, so the outline will be, I will talk roughly about an hour about GAMs, or statistical modeling in general. Then maybe we have a coffee break. You might need it afterwards. Before I have like a half an hour of population modeling. And the exercise will be, I have R code for you. You will do this in R. I mean, if you have like programs like SPSS, you're more than welcome to try that out as well. Otherwise, use the R code. You all have to have installed R on your computers. I will divide you in different groups, and I also want you to present what you did to the others. It's a bit also that you might have no time to do all the exercises, and if a group presents what he kind of didn't make in this short time, you also have this little bit of a learning effect. And I think often you do more or something if you have presentations. We might want to do this presentation then after lunch, depending on, maybe you're very fast and it only takes you 15 minutes for your exercise, could be. But for those ones I have, they get into the group with the more difficult exercise. Okay, so as I said, I will start from linear models to non-linear, additive, non-additive. Because I think like you have to know the basics. In statistical modeling, it's much easier to capture if you think about linear models. And most of the things that are important for linear models are also applied to additive models. But there it's become more difficult to understand. In general, those statistical models they have a response variable. You want to explain the variation in your y variable, also called the dependent variable. And you have a predictor, called sometimes also covariate. That is an independent variable, and this factor tries to measure, or this measured factor tries to explain all the variation that happens in y. This can be one or can be many. And the data can be, on both sides, can be continuous, but it also can be categorical data. And you try within this model to describe how the relationship is. All of those models, like now starting with the linear one, have this kind of equation. You have your y on the left side, and on the right side you have a constant. You have one or maybe two predictors and a coefficient that links your predictor with your y. And important, and that is really the most important part of the entire system, you have an error term. Because if you think about it in school or like in university, I always learned you have y and then comes beta times x. This is how I learned, this is how linear regression looks like. Probably you too? Yes? But then they always forgot that there is an error term. And this is why in the linear model, linear regression might become a generalized linear model. And why sometimes your model is not appropriate at all. This is the main factor here. Yeah, so the constant is then like the mean, or if all the x's are equals to 0, or it's the intercept if you plot it on a graph. So the coefficient graphically is the regression slope, or can be also treatment effects if you have a factor only. So now a very important part also to understand what an additive model is. The term linear means it refers to the combination of how you put the predictors together. You have a series of parameters and you combine them linearly. That means none of the parameters appears as an exponent or is divided or multiplied by another parameter. So, as an example, all those models are all linear models. even like if you have this one here, it means you have included a polynomial in the model. It's still like it's the power of 2, and if it would be the power of another variable, then it wouldn't be linear anymore. Log transforming x means still it's a linear model. Interactions, it's linear. If you take the exponent of x, or if you have a sinus curve, this is all linear. So this one wouldn't be linear, for example. Again, intercept your coefficient, one predictor, but then you have an e function with the power of 2 different other predictors. So as soon as you see something like that, that means it's a non-linear model. So now splitting up a little bit this components of this equation. So y in the error term, they are considered as the random component of this equation. The coefficients and your predictors are considered as systematic components, and then you have a link function here, this equal sign. When thinking about the random model, so you have a response variable that will show like variability and fluctuation. So it's nothing you can it might be partly randomly distributed, and this can be, as I said before, it can be a continuous one, or it can be also categorical data. So you have this error term, and this is gives the probability distribution of your response variable. And the distribution can come from any kind of the family of the exponential distribution, meaning it can be normal distributed, gamma distributed, negative distributed, binomial, for example. And this defines, and it's also defined by a mean and a variance. So to give you an idea, like what it means is, if you think about, if you look from the top of, this is your x, the predictor, and this is your response, the y. I have to make it 3 dimensions, so this is why I have a... So for example, you have on this plane, you have data points. And you could try to fit a linear regression, like a line that goes through those data points. You see, when you're thinking about you're looking from the top on that, your line won't get through all those data points. They will all be like laying next, like on the left or right side of this line here. You know that you sample one station one time, zooplankton for example, one time you get 100 individuals per cubic meter, next time you get 1,000. And then you do this constantly, you always get different values. If you do, for example, a linear regression model, your assumption is data is normally distributed. If you think of like normal distribution, often they say it's, can get of this kind of graph. This is y and x. And all the y's are normally distributed along x. This right, is that what you have in mind if you think about a normal distribution? This is what you usually think, but it also means that if you make this line, you're assuming that whenever you sample for a particular x value, for example here, that your predicted value, y value would be this here. But you know that sometimes you get different values, and those different values that you draw from the same station or site for the same x value, they kind of will distribute normally around this predicted line. So whenever you take a sample for x, you get a value that will be within this normal curve. This is what you assume. If you have count data, it probably won't happen, and your error will be quite high because it's often Poisson distributed. It has this kind of curve. So you get much more values on the left side of the line and not on the right side of the line, for example. So you're making, since you're rather try to model the mean of this of all the values that will be around, spread around this line you're making. And the values you have measured, in fact, should be within this normal distribution curve. So these are like the assumptions you make when doing your linear model, and according to those kind of assumptions. And usually, if it's normal distributed, means also that the error term is the observation they come from a normal distribution, which is the mean here. The mean is always set 0, and then you have a variance, and this is like the spread of this of this distribution, and this will be for every x value the same. Because there are also other, like, you can change this assumption and do something with this model a little bit, and then you assume, for example, that the variance increases with the increasing x or something like that. So then you come to the systematic part. On the right side of the equation can be one or more predictor variables, again continuous or categorical. Here there is no interaction included, but you can have them interacted. And you can also use, for example, polynomial terms. And the parameters here are fixed, but unknown for the population value that you want to estimate. Okay, so I told you a little bit about, this is now the error term. This is the assumption you're having for the error is important for your, when it comes to the link function here. As I said before, if you have this equation, you don't model exactly y. You model the mean of all, because x is drawn from a population, and this population has a mean, and you kind of make an assumption of this population mean, where your explicit y comes from. So there are 3 different kinds of links. One is you're assuming normal distribution. So it's called also identity link. You just model the population mean. And this is done in linear regression, ANCOVAs and ANOVAs. ANOVAs are also called they belong to the same family. They're also called general linear terms. Sometimes they were always in older statistical books treated as separate models, the different type of models. But nowadays they're combined as one, like as general linear models. It's just like this here is a factor. If you have an ANCOVA, it means the analysis of covariance, this analysis of variance. It means that you have x1 might be a factor, and this is a continuous variable. You mixed it. Then there's also another link, is the log link. You don't model the mean of the population, you model the log transformed mean of the population. You do this when you have non-negative count data, for example, and you're assuming a Poisson distribution. Or you can have a logit link. You model not the mean of the population, also not the log transformed. You model the log transformed odd of a probability. You do this when you have presence-absence data. And those ones here are also called Poisson regression, for example, and this is often called a logistic regression. And those 2 together are called considered as generalized linear models. For example, why is those links? Why are they important? If you have, for example, where was this? That was the one, right? If you have a temperature gradient, for example, and you measure the presence of a species, and you have presence or absence data, then you get probably maybe a plot like this. Like lots of data values here, and then only a few on here. Whereas at lower temperature values, they are hardly present. This is 0, this is 1. But at higher values, you have then again, for example, there's not much in the middle occurring, but at higher temperatures you have, again, high occurrences. This is usually if you have binary data, typical plot you get. You can approach, what you can do, you cannot model and say, oh yeah, I know at this particular site it will be present or it will be not present. You cannot make this kind of prediction, but you can say there's a certain probability that the species will occur. You can approach this by a linear regression, by drawing a line through all that, and then having the things only. The constraint is that maybe you model your y variable by something. The y has to be between 0, it's constrained, it has an upper and lower limit, it has to be between 0 and 1, which you never would get if you do a linear regression. You get probably higher values, a lower one. So that the way around, somebody found out that if you take the odd, which is the probability to be present, divided by the probability of not being present, this is called the odd. Also, when you gamble, you talk mainly about the odds of something will happen. This has already the constraint that it doesn't have. It has an upper limit. It goes up to 1, and it goes. No, it has an upper limit now, but not a lower limit. And if you want to have a constraint, also that it can have also negative values, for example, if you take the log transformation, you get rid of all those boundaries. So whenever you model something, you don't model your y, you model this, and then you have to, there's an equation how to, you can convert this eventually to get your original probability of y. So this is there are certain constraints sometimes what you can model, so then you model something else, and then you have to kind of reverse it to get your original y. You do this, and this is then called a log-it link for logistic regression. So when you do any kind, even if you do a GAM, it doesn't matter. First of all, you will need to know what do you want to model it linearly or non-linearly, but you also need to know what kind of data do you have. So you might end up with rather a generalized additive or linear model. So to differentiate, again, the general linear model means y is a continuous variable. The term general means that it can be, the predictor can be categorical and continuous, but only the predictor can be. It has to be normally distributed, it's the identity link, and also important, the parameter estimation is called ordinary least squares. The other ones have the maximum likelihood estimation, and if the assumption holds, then it's the result of it is the same. And again, regression and ANOVA are considered as general linear models. With generalized, now also y can be categorical. You have presence or absence, or you have proportional data. And it can be any now exponential type of distribution. It's either the log or log-it link. And also, when you do the model, then in R, for example, you say it asks you for the family, and then you can say it's, you don't say which link, but you say which family, and then it knows which link to use. Okay, what kind of predictors are there besides categorical and continuous? So there are fixed predictors and factors, and there are random predictor and factors, which is also important to know. The fixed one means that all values of a predictor variable, for example, are of interest, and you use them in the study, or all levels or groups of interest are used in the study. For example, if you want to have, if you want to know, like, around the shoreline, if like in the intertidal different zones, and if you want to know, if you use those different zones, then you can make predictions. You use the ones that are really interest you, and then you get a relationship for those zones, but you cannot make any extrapolation to other zones. It's the ones you tested, that's it. If you use a random variable, a predictor, then you try to get a random sample of something. For example, if you want to estimate the entire you want to say something about the entire coastline of Sweden. It doesn't work if you just use one or two stations and you think this is representative. You have to take samples from different kind of habitats, and then you have to use randomly sample lots of them. And then if you do this, then you can make also extrapolations of all the stations that you haven't sampled. And usually the one that you also do within the exercises, most of the time you have fixed ones. And sometimes, well, especially if you do experimental work, it's important how to consider the random one. If you start including them, then you get into the mixed models. An advantage of using a simple linear regression is that it's considered as the mother of all models. Everybody knows what you're talking about. Everybody understands you right away. But if you, for example, don't know how the relation is, which is the cause and effect, then you're not running a linear regression. You should run a linear correlation. And the overall aim is you want to first describe the relationship between both y and x. You want to also, this is one thing. You want to know how much my y increases if x increases. Another thing you also want to say, you want to explain how much of the variation is explained by x. Why? Because then if you find out that 100% of your variation is explained by x, then you know nothing else matters. If only 10% is explained, then you know, well, there might be another, a better key variable that really explains what you're talking about. Yeah, you're great, you found a relationship, but there's so much fluctuation around that relationship that it doesn't really matter. Maybe you should consider another variable or another predictor. And also, often you want to make predictions for other values, x values you haven't sampled. Within, of course, only within within the lowest x and the highest x values you have looked at. So interpolation is okay, extrapolation, be careful. If you do those kind of models, it doesn't matter if, most of them are also very important for GLMs and GAMs in general, no matter if it's which distribution you're looking at. If you look at a normal linear regression, of course you want also that the response and the error terms are normally distributed. Or if it's a Poisson regression, you want that they have a Poisson distribution. Another very important part for all of those models, and it's very important, it's the homogeneity. Sometimes if you do an ANOVA regression, sometimes you can say, it's not so normally distributed, it doesn't matter so much. Normality is not really what really counts. What counts is homogeneity. And you really want that this variance, which I show you that you don't want that this variance, this normal distribution of the small error terms, that they become bigger along this gradient. Because if it does, that means that also your standard, when you get this output of your regression, that means that they are the standard errors and the p-values you cannot count on them. You see there's a significant effect of your predictor, but in fact it's not. It's just driven by the heterogeneity in your variance, and it just tells you there's a relationship, but actually it's not. So very, very important. Another very important one is independence of the residuals. You test this. You can also test a little bit beforehand, and you do this definitely afterwards. And independence is sometimes, of course, you know already that there might be independence if you have a time series. They will probably be temporally autocorrelated. If you do a spatial distribution, they are also probably spatially distributed. But sometimes they are less strongly autocorrelated as you would assume. And so you can, if you look at the plots later on and you don't see a pattern, then it's also okay to go for it and just assume there isn't really a correlation. You assume also that in a linear regression, you assume that your x is always a fixed one, because if it would be random, you would end up with a mixed model and not a normal, like a generalized linear mixed model, for example, and not just a generalized linear model. So there's this mixed in between, it's added in this kind of abbreviation, and this became very, very popular nowadays. A lot of people think it sounds very fancy, but it has great advantages, but it just becomes statistically and to understand much more complicated. And for the linear models, it's important also you assume linearity between x and y. What happens if you don't have a linearity? There are certain things you can do. One thing is, well, maybe you should add more predictors. If you add more predictors in your equation, you might end up with a linear relationship between your y and each predictor. It really happens. You can also include interaction term, maybe, that also linearize the entire overall relationship. You can transform your data. You can also include nonlinear effect, for example, polynomials. You're still within a linear model. Or you apply just a nonlinear model, or you apply smoothing models, additive models. Starting now, sometimes it's really important, maybe you don't want to do this additive models alone, maybe you really want to stick with a linear one. And then sometimes it's also good to do so. And then you just do a transformation. Actually, this is something where it happens often that people are doing transformations. This is a typical length-weight relationship. It always has this exponential increase. And for most of the species, this relationship holds that the weight is a function of the length to the power of 3 and a certain coefficient. And this one is species-specific. And if you want to make a linear regression to know how strong the relationship, you can also, you want to end up with a straight line, you can do a transformation by both by the explanatory and your response variable. Because if you log trans within this equation all of those parameters, you get this equation here, and this is then the same as this one would be then your y, the log of k would be then your constant, and then you have this. In this case, it would be 3, and then you have this L by the power of 3. You get this. Then you have a constant here which you don't know yet, times the natural log of your length. And it's exactly, it looks like this linear regression. You can do this, run this here, and then predict, always get different values for y, for example, for each length you get different y's, and then you have to back transform, of course, to get your original weight. This is one way of saying, okay, you can do a very simple model and then just back transform. So often power function become always linear if you log transform both variables here. There's a general, and I think this is quite a nice plot, there's a general rule how you can transform and what it does. If you, for example, if you have this kind of curve, you can either transform your x variable by the power of 2 or 3, or you do this with y by the power of 2 or 3. This is an example, length and biomass. You have this exponential curve. We are here in this field. So what you can do is x by the power of 2 or 3, or you log transform y, or you take also the square root here, by the power of 0.5, 0.3. This is what you can do. This was done here, for example, and in this case here, x is transformed by the power of 2, and then you get this result. Do you think it's a great transformation for this case? Yeah, it seems like not enough. So another variable way could be then instead changing y. And for example, here it was log transformed. But sometimes what happens, you over transform, and now it's not even linear, now it's the other way around. And then you can see again, now we're getting to this field. And what you do when you have this, you can also log transform x to straighten it up. And this they have done here, and then you get a nice straight line. So this is a nice way of, if you have a curve and you don't know which transformation to use, to kind of orient yourself which of it. But in general, you want to rather transform, always start first with x, with your predictor, because you might get lose a lot of information in your y. You try to keep it as it is for most of the time. So go first rather for x, try to see if you get a linearized, and if not, then transform also your y variable. But if instead of doing transformation, you can also include polynomials. For example, if you have rather a bell-shaped curve, then a second order polynomial would be suitable, which means you still have your same predictor, but now you you take it by the power of 2 and multiply it with another coefficient that has to be estimated within your regression. The constraint when you do this is still that, as in any other linear regression model, this makes already an assumption on the actual relationship. It's supposed to often show a poor fit. This is what statisticians say in some books. They lead to numerical stability problems, and those cubic polynomials tend to have also misfits at the edge. So now, in general, why is it suitable sometimes to use linear models? As I said before, it's well established. People really understand right away also and can interpret right away a constant in the coefficient. They are if you do interactions, for example, if you include factors or several variables, then it's still you can understand really what those interactions mean. If you start with the GLM, with the binary one, and then you start interaction, at some point you really don't, you cannot really grasp it, it's not really handy. So sometimes you really want, depending also who you want to address, then you rather want to stick to this one here. You can extend this by including lots of different, you can modify it by using other link functions, fixed and random effects can be included, correlation structures as well. As I said, then you end up with a GLM or GLMN. Anyhow, sometimes even if you do transform, they not get linear, whatever you do. And you also don't, maybe then you include polynomials, it doesn't really work out. And so you have to do something else. One solution is then using nonlinear regressions, or the so-called nonlinear least squares, NLS. And there's also, I think, in the base, you don't have to have a certain package. When you do R, there's an NLS function that does that for you. And it's quite nice if those non-linear functions are already known. For example, they're for example, if you have an asymptotic curve, there is, for example, the Michaelis-Menten curve, which might be suiting your data set, and you still want to you rather want to use this one because everybody understands it in that context. You're applying it. If you have an S-shaped function, then the typical one is a 2-parameter logistic one, or if you have hump curves, then it's the bell-shaped or the Ricker-shaped curve. So there are certain functions that people already know. Yesterday, for example, Oyvind was showing us the Holling disk equation. Also, that's a function that people know. And if you're dealing with exactly that, handling time, a functional response of a predator, you might want to not linearize it. You might want to exactly, you see also this kind of asymptotic curve, you might want to use exactly that equation. This was just an example of, for example, jaw bone length as a function of DRH, and you have also an asymptotic curve. But an asymptotic curve means not always it's the same. It doesn't end up with the same equation. This one could be explained by this function here, and this looks different to Holling's equation. And the nice thing is, if you have already a similar curve as predicted by a certain equation, and you still want to stick to that, you can, for example, use in R, say you want to have this NLS function. You define in this R function, you define the parameters. You tell R, this is my equation. And what this model, what R should do, is identify A, B, and C. Because also with the Holling equation, remember yesterday he was showing that what actually varies, but what is species specific is this search efficiency, which is a function could be defined by the area and the speed you're searching through the area. This is species specific, and if you do this kind of model in R, this is exactly what the program should find out for you. What is the volume? What is the speed? And then the only thing is then you have to define a certain function and you have to have start values. And then based on those starting values, R tries all different kinds of combinations out and always looks at how much the predicted values deviate from your original values. And then based on a certain criteria, it tells you at the end, these are, the constant A is 1, B is 0.5, and the coefficient C is that value. This is also a nice way of if you have already a function you want to apply. So, and then again, the advantages, you get parameters, you get also standard errors for these parameters, and you can use them for other purposes. Or you can write it down in the equation in the paper, and people can extract right away those coefficients and maybe apply it for their models. But again, the disadvantage is that you have to specify the function right before, but maybe sometimes you don't really know the function, or you don't know, like you don't really care about the function, you just want to see if there is a relationship or not. So another solution would be generalized additive models. They have been developed rather late, now in the 1990s, by Hasty and Tibsharani. And yeah, what is nice is because y and x don't have to be linearly related, and you don't need any theory or any mechanistic model assumption. So what you do is you don't link y and x by a coefficient, but rather by a smoothing function. And this, it's mainly not model-driven, but it's data-driven. The smoothing function is estimated from your data that you have. But again, you can use all different kinds of error families. You can also do, this is why it's also called a generalized additive model. You can use a Poisson distribution, binomial distribution, and so on. I will talk here now only about normal distributions to make it easier. So coming now to the principle of what is smoothing. For example, you have an explanatory variable here and your response. And they are kind of, looks a bit like linear, but kind of spreading around a linear trend, or maybe that's quite rather stable and then it seems to decrease here. So maybe if you think like this is important and you feel like there's not a constant decrease, you might rather want, for example, to use a gum. So what would be then the smoothing value for example, an x value of 40? There are different ways of doing it. One is called a running mean smoother, and I think it's also the moving average smoother, but sometimes I heard both names at the same time, and to me it seems like they are the same. So imagine a box drawn around your the one x variable you're interested in. A certain number of data points are included in the box, and you calculate a mean. And you can do this is why it's called running. You do this because this box moves, like is starting here, and then it always includes another x value and takes the first one out. And so then you get means from those boxes for the entire series here. Another way of doing it is called a running line smoother. Within this box, you apply a linear regression. And then your smoothing value for x is the predicted one based on the regression. Or you weight, what you can also do, you can weight those data points, and the ones that are closer to your x, the ones you're interested, get more weight, and the one furthest at the edge of the boxes, they get less weight. Then you end up with a LOES smoother. And this is like how it looks like when you go through it through the entire time series. So an LOESS, it stands for locally weighted regression smoothing. It must have been something else before because I don't really understand the abbreviation, how this is coming from. But there's also the LOES. Sometimes it's also called LOES with a W here. Anyhow, this is one way of doing it. But the question is also, again, how big should this box be? It depends really on how big the box is, how your line will at the end look like. And another thing is also what happens at the edges of those boxes. thinking about this box width or span width, also how it's called. A span width of 0.7 means 70% of your data points are within that box. A nice thing is that because you include so many, you have little variance between the different boxes, but it's also you don't have a good fit. For example, like it doesn't really go. It's quite rough, like very, very smooth. Here, this is an example, 0.7. Yeah, it decreases and stays here, but it doesn't really take into account like all those data points here. If you have 30% only in the box, 0.3, it follows much more the different data points. And here now it depends on your question. Maybe you're not interested so much in exactly how much it varies. Maybe this is exactly what you want, so then you can have it, then you rather make it big. And this is 0.5, which is in general the kind of conventional value you use to have as a compromise between the variance and the fitness. And this comes as a smoothing function from another way, not from the LOESS, but from regression splines. So what are regression splines? Again, you split your x variable here, for example, depth, by into different boxes or bins. Here, for example, 4 bins. And instead of doing a linear regression, a piecewise, like a polynomial regression is applied. And then piecewise because you do this piece by piece. And after you have done this polynomial, then you get fitted values. And the thing is only, then you somehow have to glue those together, because here you see, I hope also in the back you can see, this is the fitted value from a cubic polynomial in that box. This one is from that box. But here you see, there is an overlap. It doesn't fit together. So in this regression splines, there have to be some constraints to make sure that those ones are smooth. These are called also knots when the bins are connected. Those knots, it has to be smooth, and they really have to be connected. And another constraint is also the end of the entire data series, that sometimes you get spurious behavior, and to avoid this, one way is, for example, in the natural cubic regression spline, you have you fit a line beyond the x, the last or the biggest x value, and outside of the smallest x value here. So again, you have the problem like those knots, the number of knots you have. You can also let that vary, and the problem is you don't want to have an overfitting. You don't want that the smoother goes from every data point in the next one, because you want to get a broad pattern and not explain greatly your data points. You want to say something also about maybe other data points. So to avoid this overfitting, there is a penalty term added to it. And this penalty term also reflects the degree of smoothing you have in this regression. And the GUMS, in addition, and this is in general what the GUMS, there are also regressions called spline regressions. It's exactly what they do here. They are hardly applied because usually people are applying a GUM. It's the same thing, but it only has this constraint of trying to compromise, like try to avoid overfitting, and it includes this penalty term, which is this here. This entire equation is also called the penalized sums of squares. In general, if you do a linear regression, and you have all the data points, let's say you have them around this here, you can also have you could have a line going like this and a line going like this. So usually it's estimated which of those lines have the smallest deviations of residuals, and this is always you don't measure like the deviation itself because they will always end up as 0. You use the square of that. and this area here, and you sum it up, and this, like, you try to have this as low, as small as possible. Same thing as here. This term, penalized one, you want to have it as low as possible. And this penalized sums of squares, you can divide into two parts. This is the actual sums of squares. You have, from your observed values, you subtract your predictor variables and the coefficients. But now it's not only one coefficient, it's a coefficient for every x you have. And again, by you square it and then you sum it up. But now we have this penalty term. This here is, you have, like, one is, you have a value which is called, or a term that is called lambda. And this is the integral of the second order derivative of your spline smoother, which is, this is your spline function. And the second order, you calculate if it's the higher, the more non-smooth the function is, the higher this derivative becomes. And if you have a straight line, then this second order derivative equals 0. So this is only describing how much non-linear, linear it would become under this, assuming this kind of function. And depending now on this lambda value, this tries to put some penalty on the smoothness here. If this is small, it means it doesn't put any value or penalty on this one, and it is allowed to stay non-smooth. If it becomes really high, it puts penalty on the term, and it compensates for, like, it makes this actually non-smooth term, it makes it smooth again, and then you rather end up with a linear value or linear line. And the question is, this is something like it tries all the different kind of combinations, and then the question, like in GAM, in the program, it tries to estimate which is the best lambda value to reflect the relationship you want to find out. This is something you can do either manually or the program does it for you. First, something about the type of splines. You have to actually know only two, really, the ones that are most common. The cubic regression spline, as I said, this is a third order polynomial, quite efficient. They have required knots also, and these are often for example, chosen automatically for you. If you have,
what do you mean by that? No, you said it already.
Yeah, this makes a difference between the thin plate regression spline, that these have no knots in the sense of how I explained it before. They modify it to something I don't understand anymore, which this is I don't explain. So these are like the knot assumption, like the framework I explained before. This applies here to the cubic regression spline. And as I said, for the edges, a natural one just forces a linear fitted line beyond the edges. Whereas, for example, this is important if you have monthly, you want to look at the annual cycle of something, and you look at Julian days. You want that the end of the curve. If you have something like this, you don't want the smoother, like this is January and December, or like this is the first day of the year and this is the last one. You don't want to have something like, because then it jumps so much from the next into the next day, and then it's such a big gap. Okay, I have to go later on to the outcome is of a GAM is a partial plot. Okay, I will talk about this later when have you seen a partial plot. But the thing is that the values here at the end and at the beginning shouldn't be very different. So a cubic regression spline ensures that it smoothly goes from one value to the next one, so it's at the same level. So usually people don't use it, but if you have seasonal data and you look at the entire year, you should rather consider this one. The thin plate is the default in R. But in most of the publications, I rather saw that people have applied the cubic regression spline. And I'm not sure, because sometimes I also notice that people just use the default and they say that it's a cubic regression spline, but then in fact it's a thin plate because this is the default in R. They are more linear and they are more costly computationally, but so if you do have large data sets, you try to avoid using the default. Then you should rather use the cubic regression spline. There are some others which you shouldn't really, like, you don't need to apply. But the thing is, and this is why it's one of the exercises you would do, try those different ones out, but you notice at the end they look not much different anyhow. So yeah, it doesn't really matter. You can use that one or this one. Just try. Also, if you do it later on in your own models, play around with that and see if it would make a difference. And if it doesn't make a difference, then maybe you look up in the literature again which one you rather choose for your question. As I said again, so this lambda value, that has to be estimated. How much is allowed, smoothness is allowed in the model. And this amount of smoothing is sometimes also called as effective degrees of freedom, and this is a mathematical transformation of your lambda value. You never get a lambda, you always get at the output an EDF value. And if it's higher than 8 or equal 8, that means it's highly nonlinear in your output. An EDF of 1 means that it's a straight line. You could also, in fact, apply a linear regression. How do you choose the amount of smoothness? 2 ways. One is you have it fixed, you apply several models, and you say EDF of 1, EDF of 2, EDF of 3. And then you look at the different models. You use either an AIC as a criteria, for example, or you look also at the residual pattern, or you look how much the smoothness is there. And then decide based on that, or you have you use cross-validation to estimate it automatically for you. This is important. Like usually you go for this one because it's anyway implemented in the R package. But you might, for example, I did now for one of my papers, I wanted to look at temporal trends, and I was only interested just broadly if there is rather over time an increase or decrease. I didn't want to know if it goes up and down and up and down, so I restricted it very much to a low value and wanted to know like sometimes you don't want to have the program tell you how it looks like. You really want to set it up and say, okay, assuming just a slight nonlinear trend, how much would that explain in the variation near y? Okay, so what is cross-validation? Like when you get the output in R, you get a GCV value. This is a generalized cross-validation value. It's a modified version of the ordinary cross-validation. And the general principle is you take from your data set 1 point observation out. You estimate one lambda value is picked, one fixed, and it estimates the smoothing curve. And then predicts each y value. And then it does that again, but leaves out another observation. And it does this like lots of times. And at the end, and each time it does it, it also, when it predicts the value, the y value, it also estimates how much the predicted ones deviate from your y. So this is for one particular x value, the smoothing function, under a certain minus where one value is taken out, and under a given lambda value. And if it does it with like lots of times, let's say 1,000 times, you can sum all those different deviations, you can sum it up, square it, and sum it up, and then you get a cross-validation value for that particular lambda one. And as I said, if you want to have a smallest CV value as possible. So the program does this for lots of different combinations, lots of different lambda values, and then looks which one is actually the best. What you can get out, but you never really see it in your output, it's like in the background it does, like you can get also a plot of the different, if you have different degrees of freedom, then you give different CV values, and it seems which one would be the best to explain, or which degrees of freedom explain your model best in the sense that it captures most of the variability, if you look at this graph. Yeah, if you have a 4, then this CV value is really low, so this should be then, and yeah, if you get the output, it will probably be an EDF around 4. So this is like one thing, like you have your GAM model, you have your predictors, and then the model usually tells you yourself, like you have either you want to constrain it a little bit, how much smoothing you want to allow, or you just say, choose yourself, and then you get your final output. And then that's it. Then you see if it's significant or not, and how much it can explain the variability and why. And then you can also look at the plot, how this non-smooth, like non-linear curve looks like. If you have, for example, several parameters and you don't really know which one should be the best, you have to do a model selection, as similarly as with the GLM. And the problem is also the more parameters that you have, you end up with lots of different combinations. And I think, I don't know, it was Oyen, somebody mentioned yesterday, the day before, the principle of parsimony. It's also called...
Benjamin.
Could be, yeah, it's also called Occam's razor. That was an English philosopher in the 14th century, I think. And he stated that for a given phenomena, if there are several different explanations, you always should go for the one that is most simple, because this is probably the real one. And they call it a razor because he shaved it down to the core principles. So what are the principles? First, should have as few parameters as possible. It should be minimally adequate. Of course, that requires also some ecological knowledge on your model. And the explanation should be also preferred, like rather also like not only how many parameters you have, you need, for example, you need also an explanation for that, and that also should be as simple as possible. So you need somehow a search procedure which model should be the best. There are different ways. You can either look graphically and decide graphically like what you like best, or you can also use criteria as this generalized cross-validation, which is anyway the output of in your summary in R. There's also, and this is only something you get if you do additive models. There's also the AIC, ICACIS information criteria. This is actually nice if you want to compare, for example, a linear model with an additive model, because with a linear model that doesn't calculate a GCV, but you can calculate for both an AIC. Also, if you have include correlation structures, for example, in your additive model, and you want to know, is it better to have it with a correlation structure or without, then that is a mixed model with an additive mixed model, or just an additive model. Again, mixed model won't give you a GCV, but you can get an AIC. Another criteria you also can get with additive models is the UBRE, the unbiased risk estimator. That is a modification of the AIC, but this is rather like you can apply it if you know the variance, and I hardly see it in the literature. It's mainly the GCV or the AIC that people use. Another thing also you have to consider, you can do a backward model selection or forward model selection. Forward means you start with a very simple variable, you just include one variable or one parameter, and then see which one is best. And then you keep this predictor in, and then you add the other ones. Or you take the backward selection approach, you take all 10 parameters you have in, and then see which one is significant, or like take one out, and like from the 10 you take all 10s out, and then so you end up with 9 parameters only, and then you use an AIC and see which one explains it best, or which AIC is highest, so this parameter, if you would have included it, would be not as suitable, so then you go for the one that it has a lower AIC than the one including that particular parameter.
Excuse me, do you know pros and cons with forward or backward selection?
What I do is I do both. Yeah, and sometimes I do. like one is like I have 3 approaches. I do forward selection, see what do I end up with. I do the backward, see what do I end up with, and then I also do the forward. I see what I end up with, and then from there on I also go backwards again, forward again. So like you try all the different combinations. I mean, this is one thing you can do this. Like you can either say you want to apply different models and then look for the best one, and then this is the one that you present. Some people say also you don't know which one is the best one, so ecologically you should decide from the beginning which one you want to use. You bring it down to 5 different competing models, and you present all 5, and let the reader decide what he thinks or she thinks is best.
It can also be a problem if you do run too many statistical tests. That's not good all the way. So sometimes it's good if you decide before what you believe biological is the best.
Yeah, that's the thing that I was also taught, like in statistics. If you do hypothesis testing, you base it on the p-value. Means like the probability of being wrong, you try to limit it down to 5%. But still, there is a 5% chance that you're wrong with your assumption. And if you do this several times, you increase it a lot. So then at the end, if you try 100 comparison based on the p-value, and you have 1 at the end, eventually, you have 100 times used a 5 probability chance to be wrong. And so in general, like you might have you increase it, maybe now it's 30%. So it's really highly unlikely now that this is really true, what you at the end.
Yeah, you will find a relationship if you try it.
The thing is only if you use this criteria, it's a different approach. You don't look for significance. You try to find the one that explains best your variation. And no matter if that is significant or not, you just this explains it best. So so you can do a lot of those different combinations. And I think I've seen it more recently that people have really all different. Sometimes I see like 20 in their 20 different models, and then they say this is the combinations we have, and then discuss the ones and then sometimes people also rank them. And they think, okay, we think that from out of those 21, this one is ecologically most relevant or easiest to interpret or whatever. What you also, once you have done all your model and you did your model selection, you come up with one model you think looks great. You have to validate your model. And there are 6 steps you have to do. One is you want to check if the model fit is good. You do this by plotting the fitted versus the observed values. Secondly, you want to check if your normality assumption is right or not. But as I said, you can do this by a histogram or a QQ plot. It's not that important. More important, homogeneity. So this comes from a GLM model. So you don't have standardized residuals in a GAM model. But so you take the residuals. If it would be a linear model, you can also use the standardized one. You plot them versus the fitted one, and you want to see that the spread along your fitted one is random and similarly. It's really how you have to read it. It's these are the predicted, the fitted x values. And then these are the residuals, so mostly that you have it's 0 and then plus 1, for example, minus 1. You want a pattern like this. This is what you want, which would be also totally okay, or not totally okay, but it would be okay-ish if you have and it's in the sense, yes, definitely you have more residuals that are deviating positively and really strongly from your fitted ones, and only a few observations, like the ones that deviate negatively, they only deviate slightly. With regard to homogeneity, it doesn't matter, because what you have to scan from here to here. You want the pattern always on both sides the same. So this is okay. But it can indicate you that you don't have a normal distribution. This could be rather a Poisson distribution. Like they are, if you think about, they are more like distributed like this around your fitted line.
Why don't I have standardized residuals in GAN?
At least like you don't get it
Because
without.
if you have put different variables in the GAN, don't you need to do them standardized to be able to compare them? Or are you
Well, the thing is, if you do the ordinary like ones or the standardized ones, sometimes the pattern becomes a little bit more clear if you use the standardized ones. But the general outcome, there's no function where you can do this. You have to do this then manually to standardize them. So, but it like.
But do you look at the residuals for each variable that you put into the model then?
No, you only no, it's like fitted Y. You have based on all the combinations you put in, based on all the predictors, you get a certain Y value, the fitted one. And those fitted ones, you want that the real observations you have are around those fitted ones should be homogeneously distributed. And it doesn't matter, you get this plot no matter like how many predictors you have. For the homogeneity, this is what you want.
I think I get it now.
Yeah? And again, you want independence between also the, now it comes, we want to have independence between the residuals and each individual predictors that you have included. So you also, you should also plot the residuals versus, for example, x1 and x2 and so on. And you, in all of them, what you should also do is, you should plot those residuals versus every predictor, even the one that didn't end up in the final model. Because you don't want to see anywhere a pattern. If you do find a pattern, for example, of a predictor that hasn't been included, maybe it does play a role. So maybe you should consider including it. Even if the ARC tells you the model is doesn't perform as good. But so if you see there's a pattern, you include it, you look again at the residuals against this predictor, you don't see any pattern anymore, keep it in. So this is like this graphical validation of your model. Looking at residuals, people neglect that all the time, and it's the most important thing. Don't count too much on a criteria, and this is one of the first group will look at different models, different residuals. You see sometimes patterns and what does it actually mean.
And what do you do if you see a trend in residuals?
Yes, I can come to that. And another thing is also, again, autocorrelation. For example, if you have spatial data, you want to test by using a variogram. If you have temporal data, like a time series, you apply an ACF plot. You look at the autocorrelation function and see how strong is the correlation between residuals that are next to each other, that are like that are only one time step ahead, and then with 2 time steps. And if it's beyond a certain critical level, you might include a correlation structure in your model. And another thing is also that you should look if you haven't. Sometimes you see in your data already at the beginning in a big outlier. And especially with GAN, those outliers, they can drive the entire smoother. For example, if you have something like this, you would assume a nice curve like this, but you have 1 and 2 outliers here, your smoother makes this. So when you see this at the beginning already, that you have 2 outliers here, you might think of taking them out. If with a linear regression model, you might consider transforming. But with an additive model, you don't want so much transformation, so maybe you take it out. But sometimes those ones don't play a big role in your model. So, like sometimes they do, sometimes not. So you can also leave them in and test how much influence they get. And this is by looking at a Cook's distance. It's a plot you can also see. And it should be always below 0.5, and then you're fine. So this is the ordinary outcome if you have a GAN model. You get a QQ plot, the deviant residuals against the theoretical quantile, and you have to look, you just want to get a straight line. Do you think it's okay? I think it's pretty much okay. This is a histogram which should tell you the same thing. Do you think it's normally distributed? Yeah.
It's not bad.
It's not bad, and as I said, it's not so important. Okay, now we get to the homogeneity plot. The residuals versus, they call it linear predictor, but it's the fitted value. What do you think about that one?
It's not, there's more variation in the higher the value of the predictor.
Yeah, and that's a problem here. Well, I think in general, most of people that have a GAN model would accept it. I actually do too. But I tried also, like, there is, for example, as I said here, with what you assume is, you assume that the variance is always the same. You can have another assumption. You can say that this interacts with your predictor, that it increases with your predictor, for example. Technically, what you do, you include a variance structure in your model, and then make it a kind of a mixed model. I did this, and I have to, like, there's also I gave you this one Zur chapter. It's a really actually nice book, and I highly recommend it, especially if you use R. It explains you nicely how to do all the things in R. And there are different ways, like which kind of variance structures you can apply. I applied all of them, and to me, it never worked. So if I have something like this, yes, you should have that in the supplement. But in general, this would be maybe then one solution. Include a variance structure where you, for example, assume that variance increases with your predictor, and then there are certain like different variance structures you think it increases exponentially or whatever. But this one is still good. I mean, there are some examples where you have really, like, especially this cone effect. It starts small here and then it spreads like this. This is really bad. Or if you have, if it's a straight line here, but then lots of, I mean, you also have, yeah, okay, but like, yeah, it does spread a lot. But I mean, like, you always think maybe if you have more observations, maybe you would also get some more values here. But if you have like 100,000 data points and it looks like that, well, then it really indicates you definitely it's not everywhere the same, the variance. And then this is here the response versus your fitted values, and you want to have a straight line as well. And it seems, do you think it's okay? Yeah. Okay, so you have two packages in GAN. One is called GAN, and it's developed by the two authors that developed this method, Hasty and Tipsharani. They use a backfitting algorithm. Just to let you know, I don't know what it is, but I never used the model anyway. They use a less smoother, and it's easy to understand than maybe the spline functions, but they don't do cross-validation as the MGCV package, for example. And this package, developed by Simon Wood, there you can extend it to mixed models as well. You can do a lot of other things you can't in this model. So I think hardly anybody uses this package, everybody uses this one. And it's also one of the base, you don't have to download the packages, it's in R, you just have to activate it. This is, I don't know if you ever played with R, but there are lots of functions already included. And if you want to know, like, the function is always the name of the function, then comes the bracket, and then you put something in. And there are lots of settings actually you can do. Sometimes often you don't know what they are, like what kind of settings are there. You can always look in the help file. And then the help file tells you at the beginning, gives the entire function and shows you all the different settings that exist and all the default. So I just copied that. And it tells you, okay, that's the GUM function, and then you put a formula in. Then you can say what kind of family you want. Usually it's the Gaussian, that is the normal distribution. And here you can also say binomial, Poisson, whatever. And then come all the other things. It's, for example, the method is the generalized cross-validation. You can maybe use something else. But in generally, what is the most important only for you is determine the family you want. Probably not. For now, you want only the normal, so we just keep it as it is. In the formula, you can have it written outside, or you can put this term here right in there. So you can also say, instead of formula as I've written it down, you can also say y is defined by a function, often this is in R, you have this tilde sign, by a function of s. And the function, it's a smoothing function, this is why they have an s here. This is like something you put in there, finish. But you can have certain settings within the smoothing function. For example, this is also again for the smoothing function, because this is a function within a function. You can have, you say of course, what is your predictor? You can have a k. K is representing the number, it represents the number of knots. And it's always minus, if you say, for example, k is 4, then it's 3 effective degrees of freedom you're allowing. It's not the same, like sometimes, like in general, the rule is 4 is common sense. Effective degrees of freedom, you keep it with 4. Or like maximum 4, not more. So then you should put a k equals 5 in and not 4. You always have to add 1 in. Yeah?
So what does that mean?
The minus 1 is, they do something else. The default is not using any, like, as I said, it's the automatic cross-validation. It tries all the different kinds of things out. But it has to have a limit, and it sets the limit itself depending on how many parameters you put in, depending also on how much observations you have.
So, okay.
So again, please, group number 1, try different things out. And especially also with this, the k value, to see how high actually it also can become if you have the default setting, how non-linear it would look like, and so on. But in general, it does, depending on what kind of data you have and how your model looks like, it chooses something else. And it can vary all the time. So you can also say, if you don't want it to be that, you can end up, for example, with an EDF of 8, very highly non-linear. You think, oh, well, that's too much. I don't want to have it that non-linear. But you don't want to set one specific one. You just want to say everything is okay until 4. Until 4 EDFs or until 5 EDFs, and then you put 5, k of 5 or k of 6. So to put the maximum non-linearity that you want to allow. You can put it in. Fix means it does this automatic cross-validation. It tries all different combinations out, but you can also say it's true, and you want to have it specifically, k is 4, finish. And don't try anything else. Then you have to put true in here. And then I told you that there are different kind of smoothing splines. This is defined by BS. And the default is a TP, that's the thin plate regression spline. If you want to have the cubic regression spline, it's CS. You don't have to know all that. It's also in the R code a bit, but then again, the R help file tells you. If you, for example, if you ask, look, GUM, then there are certain lists of those different arguments here. And then often there are links, for example, with a formula, then you get to this one, and then from the smoothing, it tells you also, you can click on this one, and then you get to the information of all this one, and it tells you, gives you information, what means fx actually, what means bs, so you can also look up all the things, just looking at the help file. But I think the ones that I marked blue are the ones you will play around with most of the time.
Saskia, do you think, what about the break?
Yeah, I'm done now
Yeah. Oh,
with
okay,
it.
great.
Okay. I have 4 more slides to sum it up and just show you. Should we finish this?
Yeah.
Yeah? this is just an example of changing the parameters for a K, have it fixed or not, and changing the spline. I'm not going into detail, the group number 1 should do this. But you see, depending what kind of K you get, if it's fixed or not, you get different smoothing, different level of nonlinearity. But as I said, group number 1 should try the interpretation. So what are the advantages and limitations of GAM? First of all, what is nice, it's very flexible. You don't have to a priori know what kind of response Y should have to the X. And it can capture any kind of relationship. And maybe you can also identify a new relationship that hasn't been. If you use a nonlinear regression function, then you use an existing equation already, but maybe other equation would hold as well. So you can explore a lot with GAM and then later on shift maybe to a nonlinear regression function. And you can also sometimes verify if a model is really linear by applying a GAM. You end up with an EDF of 1, which means linear, and then you know it's fine. I just go for a linear model. But the problem is it's very difficult to estimate, to understand the coefficient. In the output, you get an EDF of 4, or 4.5. Intermediate, nonlinear. What does it mean? You always have to look at the graph to understand. And this is, for example, then an output of the graph, where this is the 0 line, and you have, for a certain x value, this value here is the coefficient. You have to multiply your x value by this coefficient plus the intercept to get your y. But for this x value, it's a positive coefficient. It's a different value. So you have for each x value. So if you want to make, you can get predicted values out of the program, but it's only you because your model is already in the R program and it knows how to estimate the predicted values. But if I get your paper, I see this graph, I have to look it up myself to get predicted value for y based on your graph, and I have to look it up, and then of course it's not really precise getting the estimates from a plot. And sometimes it's nice to get those coefficients. You want to use them in other models as well. And they're also very sensitive to outliers and also gaps. But as I said, so maybe you want to remove them beforehand. And the other problem is also with hypothesis testing that they don't, like, the underlying theory of hypothesis testing, the ones you usually use, they don't work really much. So you get a standard error and you get a p-value, but be careful with that. And the other thing is that when you don't get really, like, the confidence intervals are also not reliable. So people also often say you should get them by bootstrapping.
Can you do that in R?
Bootstrapping?
Yeah.
Yeah.
I mean, is it straightforward? There's a bootstrap. Can you?
Well, the thing is, like, not if you have the basic packages, but there might be a package where it's very easy to do. I don't know the package. I do this then manually, and that's a bit of a hassle. But
it's called boot. EOT.
The function, or
The package.
okay. Well, often, most of the time, there's always a package nowadays for everything.
Okay. Would you have an example because if that's the only limitation, then you can resolve it. Well, one of the serious limitations.
The thing is, most of the time, like in the papers I look at, they use the confidence intervals from the standard errors they get from the output, and that's it.
Well, but I'm more interested in comparing, for instance, what the result, the output of the bootstrapping would say. If I could maybe just stick to the.
I had really problems actually to bootstrap it.
Okay.
So I don't have any code example to give you, but maybe I would also look up then.
I don't know, maybe that's something for linear.
Okay. Okay, so just now coming to the applications. This is, I just wanted to, like, you don't have to go through it entirely. It's to quote Venables and Ditchman's, two authors. They said in 2004 they work a lot in fishery research, and they compared GLMs with regression spline regressions and GAMs and the pros and cons. And they said, like, they concluded that GAMs are a powerful explanatory tool and also in fishery research, but that it's often not sufficient only to, or enough to estimate the fixed spline terms. Often cross-product terms I ignore. That means interactions. And it's really true. I hardly see two-dimensional smoothers, interactions within a smoother of two different covariates. It's also difficult to find a book that tells you how to do this. There are certain constraints, and it's difficult to interpret, so people avoid it. And often, but there are interactions, and in linear regression, people often do it, but they try to avoid it. So what they say is that maybe then it's better to go have a GLM and then do the interactions. Or like if you apply GAMS, you should try also interactions as well. So they have increased over the time, and almost now many GAMS as GLMs are applied. And they also now use some time series data and species distribution data. Now, yes, like I think the last days they talked a lot about additive relationships now. So it becomes more and more present. Those two-dimensional smoothers so far only have been really used when looking at geographical effects. It's interaction between longitude and latitude. And as I said, also with the GLM, you can extend them. And another thing is, you can also link them. This is what Thorsten did. He didn't really explain it a lot, but the different relationship he found for pseudocalanus and cod and spread, they actually also link the models and try to make predictions based on certain initial values, and then estimate then one value for cod, and then by that you could also estimate pseudocalanus and then back again to cod. So you can also, and I will show you in another example how you can model those, link those kind of models. This is, for example, Loppe and co-authors. He looked at phytoplankton distribution in the North Sea and different environmental drivers over time. These are the partial plots you get, and they're always centered around 0. And it's again, the lines here means the coefficient you can read. So here it's not very strong, but for example, the coefficient having a low value for the wind conditions, you have a negative coefficient of minus 0.5. Here it would be a positive one, 0.5, and then you can do your calculations. And this is a two-dimensional smoother. These are kind of PCA scores, and you see that this is like the North Sea, and here are those kind of the isoclines. You have higher PC scores near the coastlines and higher phytoplankton densities than here. But in general, it's very difficult to interpret or look at those kind of plots. Here's another example with temperature and wind, I think. I don't know how to interpret that. But what you can do is you can have a three-dimensional plot. It's the same, and then this is from different angles. And it makes you a little bit, you can better see that, for example, I think this is, the wind conditions are here low, and they increase. If the wind condition increase, here...
Opposite, the wind decrease. If you look at the one.
Oh, yeah, okay, yeah. If the wind decreases here, you get the response increases. But that depends also a lot on your temperature. It's not always never the same, and so you can get this kind of very very non-linear valleys in the mountains here. But in general, if you do this, then rather look at a three-dimensional plot. And just last thing now, because Thorsten mentioned it, now coming from additive to non-additive, a T-GAM. It only means it's the same thing. You have your y, a constant, you have a smoothing function for, here it's the distance. This is a model from Stieg et al. From the Barents Sea. They wanted to know zooplankton dynamics, biomass, explained by certain drivers, for example, the distance to the coast, the smoothing function. And these are under here, these are several coefficients for several different variables, but these are all linear. He made this linear, but this one was something he wanted to have non-linear. So, and then an error term. But in a T-GAM, you can have this equation twice. This smoothing function can differ depending on another variable, which would be fish abundance, for example. If fish abundance is below a certain value, you have one specific curve, and if it's above this variable, it has a different curve. So you can have different effects of one variable depending on another variable. This is something you don't not only have in an additive model, there are also linear models that can do the same thing. But with an additive model, this is the T-gum, and there is no code out, no package you can access from the Askö. They keep it hidden a little bit, like, or keep it to themselves, because I think they one that developed that he wants to write a book soon. And then, for example, you would get an outcome, for example, at different stations. This is in the west and east in spring and summer. Let's look only at this plot. In the west area in spring, zooplankton, the zooplankton biomass does not increase with the distance to the coast, or increase if the capelin abundance is low. There is no effect of distance. But if capelin abundance becomes high, you get an effect of the distance, which is first decreasing one and then increasing one. And then you can do this for all different kinds of stations and season combinations. And this is something I also applied, but you will see the example. As I said, I looked at long-term trends in major copepod species in the Baltic Sea. And for this I used gums to identify driver, but then also to do some model simulation by connecting those individual models. And this is what I will present you, just giving you an idea of what you can also try with those models. So in general, population dynamics are quite complex. They can, often it's abiotic and biotic drivers together, which can act multiplicatively, or they can leading to an increase or decrease of the population. They can also work counteractive. They can generate stable limit cycles, or there are sometimes also time lags from environmental effects. And those effects can also switch according to another variable, which you can identify, for example, the T-gum. Oops, there's a note of me. In general, there are two. No? It doesn't do anything. Okay. There are three different mathematical frameworks to do population dynamics modeling. One is if you have continuous time models based on differential, or the ordinary differential equations. You can have also, and then they're called ODE models, or you can have continuous time models based on delayed differential equations, DDE models. That is if you include time lags also. And then there are discrete time models based on difference equation. And if you have populations that have non-overlapping generations, then it's better to use discrete, or then it's easier to use discrete time models, as they are really easy to build up and easy to understand. And still, those kind of discrete models can generate a lot of different patterns, like oscillation patterns, as well as chaotic patterns. So these models are really widely adopted in fishery research. For example, the Ricker model, the Barrett-Holt model, these are all discrete population models. However, in zooplankton ecology, most of the time numerical models are applied. And if they apply discrete models, they are based on the Leslie matrix, which is they are structuring it by the different stages, or like modification of the Leslie matrix. So they are trying really to address the population structure with all the different stage classes that exist, but they are mainly they're focusing on vital rates like fecundity, mortality rates, and so on. Not abundances are usually modeled in that approach. However, the matrix models are nice because they can be linear or non-linear, they can be deterministic as well as stochastic. But usually in most of the models they use linear equations, and it's deterministic, and hardly anybody includes stochasticity in the model. How can you do this? There are 3 different ways. You can either include a random variable. I think Benjamin did this in a second example. Just have one variable that somehow also with some numbers that to add it on top. You can have random values which you always add to your population. And you can also randomize the model parameter, the ones they are explanatory variable. For example, those mass balance models or NPZD models or whatever, they are rather kind of have a bottom-up view. They are more process-driven. They want to understand metabolism, mass balance. And based on that, you can also get population dynamics. And then there's this top-down view, which is more life history-driven, where you structure the different life history and model different stages individually. So what kind of different life cycles are there in marine plankton? You can divide them in holoplanktonic species or taxa or meroplanktonic. The holoplankton lives entirely throughout its life in the sea. For example, copepods, zarbs, chaetognats, and larvaceans, or like appendicularians also called. And you have a meroplankton, which, for example, is a lot of fish species, like they are at the beginning ichthyoplankton, and then they get to a size that they are not considered anymore as plankton. They have clams, snails, barnacles. They all have larvation stages which float around in the sea and are considered as plankton. So from the holoplankton, there are lots of different taxon that, for example, from the cnidarians, you have a lot of Cyanea is, for example, one species, Aurelia, that live in the Baltic Sea. You have Pleurobrachia, which is a ctenophore that is in the Baltic Sea. Zakita is a chaetognat that is common in the Baltic Sea. And then also copepods, the main species that I'm looking at. Why do I look at them? Well, they are not only dominant in the Baltic Sea, they are the dominating species all over marine systems. They have quite a big range from 0.5 to 5 millimeters. And since they are so dominating, they play a big major role in the energy flow in food webs. They also, because they are so diverse in abundance and size and species diversity, that they are also considered as the insects of the sea. They inhabit all different kinds of environments. They are not only in marine systems, also in freshwater systems, but often cladorcins are more dominant there. And they can occur at temperate or polar regions as well as in tropical regions. And they have been shown that they are nice, suitable indicators to show climate change effects, as they respond so strongly to temperature, have a high rapid turnover rate, and they are not affected really directly by anthropogenic pressure, of course indirectly via the fish stock, but not directly. It's nice to see what kind of effect the climate has on the marine system. And in general, they're considered as bottom-up driven. So the copepods have a complex life cycle with 11 stages. These are the 6 nauplii stages, like eggs, and then the nauplii stages. And then come 5 copepodite stages, and eventually they mature to adults. How this life cycle is over the year depends really on the species. This is an example of Calanus. I think Oyvind showed yesterday also a picture of the life cycle. You see that in winter you have a lot of copepodite 5 stages. Then they mature in March and April. They spawn, and then you have one cohort at the beginning of spring, and part of the copepodite 5 stages then go down, as he showed yesterday also, that towards the end of the year, they go to greater depth and stay there. But they don't do this only once. There's another cohort as well. You see also younger stages in late summer, early autumn. And then another second cohort that goes down. When it comes to Pseudocalanos, this is based on the Globic data, where they sampled the Bornholm Basin in 2002 and 2003. And you see a lot of nauplii in March, April, May, June. 2002, the same in 2003. And then progressively towards autumn, you have more and more of the older stages. The 4 and 5 stages here, for example, comprise a lot of the winter stock. So they have rather an annual life cycle. Some females exist also in summer and autumn and reproduce, but this is really little. And so far, the Pseudocalamus has been related positively to salinity and negatively to spread. And most of those models use so far only linear models. But it seems also that there is stage-specific responses towards salinity and temperature. So I want to know also how those different drivers relate to the different stages. And in general, they have a very similar long-term trends, but still the width of the long-term trends differs a bit. For example, all this is in winter and spring, summer and autumn. You have different stages. These are, for example, winter copepodite stages 4 and 5, and the females. These are the nauplii in spring and 1 to 3 copepodites. They all show rather a peak. This is, you cannot see it, sorry. This is like this from the 70s to the 90s. But the increase is really early here, for example, with the younger stages in 70. But with the older stages here, the females, for example, the increase starts in the middle of the 70s. So they must be also driven by different factors. The same, they decrease much earlier than, for example, the younger stages. So I gave you, I don't know, I think you did, this paper from Dingse. I gave you, I think, one paper to read, if you want to, if you're interested. That was kind of the basic for my approach, because what they did, they looked at different fish species and modeled them using gum and also tea gum. And they included also the effect of the younger stages on the older stages. And this is a more common approach in fishery science, but not very much, or it hasn't been done at all in zooplankton. So I focused on the Goatland Basin, and I used the long-term data set that existed already. And because I had so much heterogeneity in my data, I log transformed the data, the abundances. And I used abundances from different stage groups, from nauplii, copepodite 1 to 3 were grouped, the same with 4 and 5. And I did this for every season. And for every season, for every stage, I used a different model. I didn't include all of that to make it not too complex. And I wanted to know the effect of the Baltic Sea index as a proxy for... I didn't have food, that was my problem. There's no long-term time series of phytoplankton. But the Baltic Sea index, or the climate conditions, are related, or known that they can be related to the phytoplankton conditions, especially the winter. Air pressure is known to drive the summer-spring dynamics, so I used this as an indirect proxy of something else. I used temperature, salinity, and then predation for the older stages, as they are known that they are eaten by spread. And then I wanted to also know how much the internal dynamics are, how much do different species depend on the previous stages or on the female that reproduce. So this is an example of one gum model. The nauplii in spring I modeled by an intercept and by a smoothing function of the females in winter and females in spring, because the sampling was only once a season, and I thought maybe the females in spring cannot really reflect the abundance of the nauplii because reproduction, something occurred in between the different samplings. So I just included both of it and then thought, okay, model selection will tell me which is the better can better explain my nauplii abundances. And then I used Baltic Sea index, for example, temperature and salinity. And in addition, I also, for the older stages, I used a tea gum, and I wanted to know if the same kind of model you just saw, if that varies between different levels of predation. If high predation exists, maybe the salinity has a lower effect than it does when predation is low. So the flow chart here with the bubbles is kind of presenting again over the entire time series the abundances, the proportional abundances in each season. This here are the nauplii, the younger copepodites, the older one, and the females, in the different seasons. And you can see right away the nauplia only occur in spring and hardly in the other seasons. And then you see already a stock building up of younger copepodites, but mostly being abundant in summer, a few left in autumn, and then the overwintering stock becomes bigger. But since they decrease also because of something. And then the females are kind of most abundant in spring. So, as I included the density defects, it turned out that these are the results, that the female abundances determines how many nauplia I have. The number of copepodites is dependent not so much on the female, but how many nauplia I survive. And so these are the different internal dynamics, who depends on which and whom. And usually this is an additive effect. It's no matter how the predation pressure was, except for summer and autumn here, with the older stages, the females, and the 4 and 5 stages. This density effect was only valid when predation pressure was low. Because if predation pressure was high, they were eaten so much, then it didn't matter anymore how many were there in the previous season. And then as I also added up, I also wanted to know how the external drivers are, and it turned out that, for example, the Baltic Sea, the local climate conditions and temperature were only important for, this is a week, if this was weekly significant, they are mainly important for the younger stages, and salinity and predation were important for the older ones. That's just an overview because you don't need to fully understand what's going on. But just, I could see a little bit, okay, which drivers are important for which species, for which stage. And this is an example of one of those partial plots you get. And for salinity, most of the time I got this type of plot. This was not usually for pseudocalamus it says that our salinity is good, is more saline, the better it is. But this partial plot shows you that there is a positive effect of salinity on the abundances up to 9 to 9.5 PSU, and afterwards it doesn't matter so much. Then maybe other factors are more important. So applying a GAM shows you also that this, although I didn't know anything about it before, I didn't assume any kind of relationship, it showed me that it's more this asymptotic curve, and I could afterwards now try to figure out and change my model and apply a function in it and see how well this function would represent the relationship. So that was what in one paper I just try to find what are the main drivers for each stage and how they are all linked together. And then I thought, well, if I take those stages that are really connected, that means also that, for example, if salinity is important for the females directly, it directly affects the reproduction, and I know that the number of females is important for the nauplia, then somehow the nauplia, the salinity effect is also affecting somehow a little bit the nauplia, and then how much does it actually, those direct external effects, how much do they propagate within the life cycle? And since, for example, temperature is also important for the younger stages, if salinity conditions are bad, I don't have many females, I don't have many nauplia, but maybe the few, and then I don't have many copepodites, the young ones, but maybe if temperature conditions are good, then more of them survive. So maybe then salinity is not so important for those ones. So to figure out how does this, since they are linked, how does that, what happens under different conditions, I thought, okay, maybe I can link all of them. So I chose only those models where I could directly see a link. I put this kind of together. And I started with winter copepodites, and I'd used one value that I know from 1960. And since I know that they are dependent on the value I have here, I could determine the females, and then I could determine the number of nauplia, and so on. And then I had the autumn copepodites, and then I could determine the winter stock the next year, and then run this for 50 years. Of course, there are also external drivers important. So I used in the first run, I just wanted to build it up, this life cycle model, and see if I can reconstruct with that model the past. So I used the observed time series that I initially used for my model. And that's to make it stochastic, I wanted to include noise. And what I used there, like I used the approach of taking the residuals of my model and randomly added them to my different abundance values. Is that clear? And then I got from 1,000 runs, I get a mean from every run and a standard deviation, and I plotted it and wanted to compare how my model run did with the observed time trends. This is now in big. So I have winter stock over the copepodites, the females in spring, nauplii in spring, young summer copepodites in summer and winter, in autumn, and here these are the older stages, 4 and 5, in summer and autumn. The circles are the observed time series, the blue line is the predicted one. And it looks like it does quite well with the older stages here, with the females, also still with the nauplii, and also with the older ones, but it didn't do very good with especially the younger stages in autumn. Initially, my GAN model didn't explain so much variation, and here, I predict almost no trend really, and of course there is a trend. So the performance for this particular stage was not so good. But in general, I could capture quite good the long-term trend. So in one step I'm not showing you, then I also tried, okay, what would have happened in the past if temperature would have been different? If the increase wouldn't have been that strong. So I tried those kind of scenarios, and I just figured out how much would it have mattered if temperature would change, or salinity, or predation, because I know that not every stage is dependent on that variable, but because of this internal loop, the overall dynamic would be influenced very much by only one environmental driver. And it turned out that salinity in spring and winter predation were really driving the entire life cycle very strong. So then I thought, okay, maybe I can also use this model to look for future dynamics. And initially I thought, okay, I just use, I make up my own values for salinity and predation temperature. But as Susa is also doing food web scenarios, I thought maybe it's nice to compare my results with hers and use similarly initial data. So I used here biogeochemical data, or from Balsam, and I used 2 different management scenarios. One is the BAU, the business as usual, an increase in nutrient load, or we follow the Baltic Sea action plan. Based on that, the output was I got salinity and temperature values, and some other values that were important I needed fish abundances for predation. So I got from Susa some fish abundances based on 2 different management scenarios, the current fishing mortality and the Baltic Sea, the cod recovery plan. And she also used some of the Balsam data to give me at the end 4 different kinds of predation scenarios. And all those ones I used then to run my model.
Saskia, sorry, but I can see the last 3 months after the temperature.
Yeah, this is something I didn't, it's hypoxic area, cod reproductive volume and primary production, something I didn't include in my model. She only, for the food web it was important, but not for me. So I didn't really care, it's just I got 4 different fisheries, fish spawning stock biomass scenarios.
Isn't primary production really important for the use?
Well, it probably is, yes. But the problem was...
I know you didn't have the data, but...
the question, even if I would get now the data, the question is, where should I put it in my model? Because I know that the younger stages are more on the surface, and the older stages are more on the bottom. And they are feeding maybe on totally different things. The older one probably feed on detritus, and the younger ones maybe on cyanobacteria.
But the Baltic Sea index, isn't that kind of... use that kind of as...
It's a proxy, yeah. But I would have liked to use the Baltic Sea index instead. But I didn't include it here. I didn't include it here, but because the problem was for the future scenario. The problem was that I don't have values for the future. So I also, for the hindcast, I thought, I just take it out. Maybe it's not so important anyhow, because it was only important for the nuclei. And the performance was okay. So I thought, okay, it doesn't, like, I included it once with, and there wasn't a big difference. So I thought, I leave it out from the beginning, because then I can do it also the future without the Baltic Sea index. But yes, exactly. And I think this is the point that I believe that phytoplankton dynamics are particularly important for nuclei, as it is indicated by the Baltic Sea index. And also when comparing Askö, Timor, and Pseudocalanus, they also live in different levels. Askö also, like the nuclei of Pseudocalanus, live in the surface. Timor, like the younger copepodite stages, they live in the intermediate water body. And it was the similar pattern. Timor was driven by temperature as the young copepodite stages. And the nuclei of Pseudocalanus and Askö, being at the surface, were mainly driven by the Baltic Sea index. So I think they are driven, there is an influence, particularly maybe on the younger stages of phytoplankton. Definitely this is a drawback of my model, that I don't have that. I could try to do this model then also on a shorter time series where we have data and see what kind of relationship I would get out of that. So then, I did this also a lot, and then I got some projected time series. This is an example of one scenario where we have follow the recovery plan in the Baltics, but don't reduce nutrient loads. We rather increase it. And then I got different results for different stages. In general, a decrease, but the decrease was either maybe a continuous decrease or an abrupt shift. I don't show you all that, but I wanted to have in a comparison with other model scenarios, and they don't use seasonal data and not stage data. They use total annual biomass or total biomass in spring, or like in summer. So I just wanted to make a comparison, and I added up all the stages from one season and averaged over spring and summer to have the main production period covered. And so according to my model, if the predation pressure, like if the fishing mortality of cod is still high, we will have rather a lot of spread, probably. So the predation pressure will be quite high. And the thing is that the nutrient load for the temperature and salinity don't matter so much. It's mainly like and for like if predation pressure on cod is very high, it doesn't also matter so much on the nutrient load, if there's a lot of food or not. Cod is reduced no matter what. So definitely spread will be high, a lot of high predation pressure. And in general, I get this pattern that these are the current levels, and it will stay until at low levels, as we have now, until 2014, then continue to decrease and stay really at low levels. On the other hand, if we reduce cod fishing mortality, then they can recover, and that means that we have also less spread. So a lower predation level. This is represented here. So it's currently high, but then predation pressure will go down in both scenarios. But that also, how strong it goes down and up again, also depends how much nutrients we have. If we have higher nutrient level according to the net fish, the food web model, that means we have also less cod, but a lot of spread that can feed because of I think it's assumed that Askö will be high also, and then they can feed a lot of them. So the spread is supposed to be higher, and then also predation pressure will be higher than here, for example. But no matter how much the predation pressure is there, here it's high, here it stays rather low, I have an increase because predation pressure goes down. It just matters, like here it's a little bit higher, the increase than here. But again, 2040, it goes down, and then it stays down even if predation pressure goes down again, it stays here. That is actually pretty much driven by the salinity, because I use the A1B1 scenario where salinity is staying here at levels like this, and then in 2040 decreases and quite sudden, and then again around 2018. So I could see with this model, first of all, by using T-gum, I could identify that there is a switch depending on how strong the predation pressure is. There can be also, salinity, for example, can have an influence on a low predation pressure, but if predation pressure is high, then salinity doesn't matter anymore. I could see this by using a T-gum, but by using this kind of model and trying to use different scenarios that haven't been seen in the past, I could also see that also salinity can be really much a limiting factor, and then if the salinity is low and reproduction is really low, then it doesn't matter so much how strong predation pressure is, because they can't reproduce really much and they stay all the time at low levels. It also shows a little bit that management strategies, like if the Baltic Sea will freshen out as much as it's predicted under that scenario, then management strategies at least don't matter so much for pseudocalymus, which will in the end, of course, also somehow feed back to the fish stock, which I haven't included, and I don't know if that is really, we will see if that is included in the food web model tomorrow. But you can see that it's quite complex, and different drivers can be important at different times, at different stages, and this can run then the entire life cycle. Huh? Yeah, there's anyway that slide. Yeah. So it showed this model that the performance was quite good and robust, which is very important if you want to do predictions. And this complex population dynamics I could capture by including all that. And I also, by adding noise to it, I could also get an estimate. That's talking about the mean. This is like the mean here, but you can also see that, for example, here there's also quite an uncertainty how much it will increase. So we might be also at levels like here, so it doesn't, like the increase won't be that strong. But at least you can have a little bit of feeling of how much that could be, like how much that could also differ in which range. It could be that if this confidence interval is going down, and it could be also that it's not really significant, this increase, as I predict when you're just looking at the mean. So this is a way of also taking into account the uncertainty. And you can also try different scenarios and like different environmental conditions that we haven't anticipated yet. But I also have to say that this model is very locally. The problem is, for example, the salinity effect I have only applies to the Baltic, to the Gotland Basin, because we have different conditions in the Bornholm Basin. They're much higher, the salinity value. So the saturation at that level I have experienced in the Gotland Basin doesn't hold probably for the Bornholm Basin. It might be at a different level. When you do those kind of regression analysis, you try to look for a relationship. But we always be aware, maybe salinity, we know that salinity physiologically has an influence on pseudocalymus, but maybe if you don't know anything about the species, the salinity effect is driven by something else. And it's just indirectly connected. So maybe this kind of saturation is saying something else, that because something else is happening at those years where we had those kind of salinity values, something else happened. And this only happened at the Gotland Basin, but not in the Bornholm Basin. So it's currently quite locally. It's also difficult. You only get a lot of curves, partial plots, and it's difficult for somebody else to get this kind of relationship and you apply it on other data. I could do it because I used in R, I did first the model, and you can do in the model, you can say, now run this model on a different data set. It has, the coefficients are stored while you're in R currently. So you can apply those smoothing function to all different kinds of data sets. But you have to do this right at the same time and save it. If somebody else wants to do it, I have to give the person my data set to train the model first. So this is like how you can overcome it. You can either you can save that model you have in a package, and then people can download the package, and then those models are available, or you can give somebody your data set to train the model on, and then apply the data set. And another thing is also, if for example, Susa wants to use my model, she doesn't get any coefficients, but we could link it. She could use my model and implement the model itself based on an RPEG, for example, in her model to run it. So this is, if you link it, it would be possible, but she cannot put another equation into her model based on my results. My model has to be somehow implemented in that. Yeah, so I put a little bit of literature. If you get the presentation, you can look that up. There's also my email address if you have questions. And I'm fast now. That's before lunch.